We're delighted this evening to have this presentation by Dr. Hans van Maanen, and I'll be giving a brief introduction now, and then we'll go straight into the presentation. So Hans was awarded the BSc and MSc at the University of Amsterdam, and received a PhD at Delft University of Technology. And during his career, he worked professionally in research and development. He is the founder of Temporal Coherence, which works on high-end audio systems. And currently, he's working on how audio equipment responds to complex signals and how this should reflect in the related design process. So without further ado, I'm absolutely delighted to hand the virtual floor over to Hans, and we'll get on with this. What is, I'm sure, going to be an extremely interesting talk. Thank you, Hans. Over to you, sir.
Thank you, and well, warm welcome and a good evening from my side as well. I'm just going to see if this works. No. Yeah, this works. Okay, well, what's the background? The reason is that many people's reviews and from my own experience, there's a pure correlation between the measured and the perceived quality of high-end audio systems. And why? So we're trying to identify the causes of these differences. And we want to stimulate R&D to close this gap, because I think it's ridiculous that almost 150 years after Edison for the first time reproduced sound, we still don't know what to measure to get a good correlation between measurement and perception. And using that, we'll try to find directives to develop better sounding audio based on the requirements of human hearing and the reproduction of music. We're not listening to test tones, I think. Jamie Angus also made that very clear. And I'll show that important directives are feasible. You can have nice thinking, but does it work? Yes, it can. Well, when you reproduce sound, there are differences between the original and the reproduced version. And I'll grab that in the concept of artifacts. So that includes more than distortion only. Distortion is an artifact, but not every artifact is distortion, and we'll see several of those. And that's why I call it DNA, and it stands for distortion and artifacts. I will try to elucidate that during the presentation, and I think it will be clear. Well, some nice paradoxes. Harmonic distortion figures of loudspeakers are order of magnitude larger than those of amplifiers. Yet the difference between amplifiers can clearly be heard on those loudspeakers. And there's a huge discussion on fora about using feedback or not. You can find anything in between none to up into the stratosphere. And well, it's impossible that both can be correct. And when you read audio magazines, you often hear that the reviewer says, well, you have to match this amplifier with that loudspeaker to get an optimal perceptual result. And why can't we do that based on the specification, which are based on measurements? If you do it on specifications, you rarely get something which sounds best. And why? And an interesting paradox is that there are differences between the CD reconstruction filters are audible, although these only occur above the upper limit of human hearing for continuous sine waves. And this is perceived even by seniors. And well, I'm not that young anymore, I have to admit, and I can easily hear it. Actually, this last weekend, I had a nice illustration of that. So what's the current situation? Well, the requirements are based on the Fourier theory applied to human hearing. But the Fourier theory is a linear theory, and the human ear is not a Fourier transformer, which was a beautiful Heiser lecture by Jamie Angus Wright in 2023. So it's an incorrect starting point. It's only allowed to apply the Fourier theory to systems which are, amongst other, linear and time invariant. Neither human hearing nor electronics nor loudspeakers fulfill these requirements. So as DNA are generated, the Fourier theory is neither capable nor suited to describe the response of human hearing and audio systems to complex signals like music. So the results of the Fourier theory are therefore at least questionable when applied to audio, but most of the time they're incorrect. And surprise, surprise, a nonlinear system is able to receive more and other information from the signal, which is good for humans, but not for audio. So what kind of artifacts can we encounter? Well, music consists of many frequencies which occur simultaneously with a wide range of dynamics, including rapid changes in time. Think, for example, the attack by percussion, but also with the grand piano. And the different artifacts can interact, leading to unexpected results. The problem is that all these artifacts occur simultaneously. It's not a matter of or, but of and. So the important questions are which techniques are available to counteract DNA and what are the consequences of these for the perceived quality assessment. Well, varying output powers lead to fluctuations of the supply voltages, which is a memory effect, causing the operating points of amplification stages to shift, which will illustrate it. And the size of the shift is determined by the internal impedance of the power supply. And always keep in mind that amplifiers have always a limited or finite bandwidth and thus introduce additional time smear, which is a direct consequence of the Fourier inversion theorem. And in most cases, it's impossible to quantify the above-mentioned artifacts by measurement using continuous sine waves. Therefore, more complex test signals are required to achieve this, and we will illustrate that later. So, can we identify the causes of these? What are the causes of the discrepancy between measurement and perception? Well, that's the £1 million question. So we have to look in more detail inside the amplifier to determine where the artifacts are generated. So I will use an approximation of the internal workings of an amplifier, which amplification and locally generated DNA can be identified separately. It's an approximation, and this is the idea. We have an input signal, then there's a subtraction circuit, and the misery that the subtraction circuit introduces is added separately as D0. Then we have a perfect amplification stage, and its misery is added as D1, etc., etc. Then we come to an output signal, and we have a feedback loop. And when you do the math for a rainy Sunday afternoon, you can get this equation. And I'm not going into much detail, except that first of all, the capacitor, which limits the bandwidth of the amplifier, is not included, because it will make things even more complicated and it will hamper the interpretation. But what's important is that the misery of the subtraction circuit is amplified just as much as the input signal. So the only the suppression of the misery reduces or increases with the further downstream of the amplifier, but only from the final stage is fully suppressed. But the law of conservation of misery immediately acts, because power stage has specific problems which often cannot be solved by feedback, and that will be discussed more extensively later. So, well, I think everybody will know this important equation. A is mu plus 1 divided by 1 plus mu beta, and well, A is the amplification in closed loop, mu is the open loop amplification, and beta is the feedback factor. So what are the consequences of what I just told for the feedback equations? Well, the two parameters are crucial: the open loop amplification mu and the feedback factor beta. We will concentrate on mu, and the question is, what is mu? Well, that's a good question, and I want a good answer. Well, first of all, it's not a constant. It will be trivial because the amplifier would not distort, as the open loop amplification would be a constant. So we have to look at the operating line, the relation between input and output signal. And you can get this graph. In yellow is the operating line. This is the input signal, and this is the output signal. And the input signal is, say, reflected over the operating line to the output signal. So you get distortion. The green is the output signal, and if it would not distort, you get the red signal, and the difference between red and green is a distortion. And a sinusoidal signal would generate just harmonic distortion, and that's usually suppressed by feedback, so it's not regarded to be roaring. But when you have a low frequency signal which modulates across the nonlinear operating line, and loaded on that a high frequency signal, you have the problem that's the amplification for the high frequency signal is the derivative of the operating line. So, and that is not constant, and it can be quite serious. Here you have the value of 118 and here 197. That's almost a factor 2 different. So you get intermodulation distortion, but that's not the only one. You won't have a constant value for the mu for the high frequency. So when you look at just harmonic distortion, you don't get the complete picture. So you have to look at the derivative, and that can only stay constant if the operating line would be a line, straight line. But an amplifier with a straight operating line will not distort. So usually the suppression of the distortion is calculated by using a constant value for mu, or in other words, we assume a non-distorting amplifier to calculate the suppression of the distortion by feedback. Where on earth did you ever get this idea? But what's mu in reality then? Well, fasten your seatbelt, please. Because mu is the product of the operating lines of the individual nonlinear amplification stages, the power stage, which has a non-constant output impedance, both amplitude and frequency domain, acting as a voltage divider with the non-ohmic load of the loudspeaker, which is not a constant, and has amplitude and frequency domains properties, and you have a bandwidth limitation, frequency domain. Well, the graphs I just showed are basically described a quasi-static system, as the frequency dependency is not included. To be honest, to get an analytical equation from mu is far above my mathematical capabilities. I have no idea how to derive such an equation. And as we are studying perceptual results from music, you'll have to use signals varying in strength and time. And this is an example of such an even still quite simple signal. It's 800 Hertz sinusoid, and we have a triangular modulation, and you get a signal like you see on the right-hand side or in the middle. And if you want to see the envelope, you have to just rectify it. And this technique has been used in AM radio for ages. This is grand pastel stories. The envelope of any arbitrary signal can be found and determined by rectification. So the nonlinearity of the operating line will also result in what I call internal local detection. Actually, it's a partial rectification, which is why I name detection. And you can see it by looking at a single amplification stage, which processes a tone burst. Look at this simple stage, just you have an input, say a low impedance input, it controls the base volume, and then you have a simple amplification stage, and this collector acts more or less as a ground source, which has a high impedance here. So, but if my supply voltage now varies, because I have a high impedance here, it also occurs at the output, because of the high impedance of the collector. And fluctuations of the supply voltages are caused by changes in the signal strengths and cannot be determined using measurement continuous sine waves because they have constant amplitude. So the supply voltages have to stay rock steady to prevent that its fluctuations end up in the outer signal. This we'll discuss in more detail later, but it's not the only cause of the shift of the operating points. If you look at a tone burst, and I've shifted the output signal and the average output signal to make it more clear, the tone burst is distorted, which means that its average value is no longer zero due to the nonlinearity of the rating line. And you get this nice shift in the operating point due to this rectification. And note that basically the shift is the envelope of the tone burst signal. And again, you won't see it by detection and looking at continuous sine waves, and that's remain hidden. And due to the internal local detection and or varying supply voltages, the operating points of the coupled amplification stages will also shift, because nowadays, when we talk about semiconductor amplifiers, they use DC coupling, and that leads to what's often referred to as unrest in the signal. So when we look at this signal, we'll process it by a nonlinear amplification stage, and we'll compare the spectrum of the input signal and the output signal. And you see this in the left-hand side, you see the toe, the two peaks. But the major difference is here. On the low frequency side, there's some rubbish, and it's quite significant because it is quite strong compared to what originally there, and we see an increase in the harmonics. And you see it more clearly when you subtract the two, and you see this low frequency rubbish, and that's caused by the internal local detection. And of course, the 800 Hertz peak completely disappears, and the harmonics increase. So the low frequency rubbish is actually related to the envelope of the signal. So a nonlinear amplification stage creates low frequency rubbish. And it's a consequence of not fulfilling the requirements of the linear Fourier theory. And it's similar for more examples, which you showed up during the presentation. Oops, sorry. Because when an artifact goes undetected with measurements using continuous sine waves, the underlying cause is not fulfilling the conditions of the Fourier theory. And of course, the capacitor, which has to be used to limit the open loop bandwidth, interacts with the internal local detection, and especially when the cutoff frequency lies within the audio band. You have to add the capacitor, and this will act as a first order low pass filter on the stage that we just discussed. And then you see that the distortion creates a quite different signal due to the filtering. There's an interaction between different artifacts. So the nonlinearity of the individual amplification stage is an important source of DNA, like distortion, intermodulation distortion, internal local detection, etc. So linearizing these amplification stages will result in a strong reduction of these contributions inside the open loop. And keep in mind that global feedback can improve the overall figures, but not the details in complex signals like music, as they already have been degraded due to the interaction between the different artifacts. So this has been confirmed by several listening tests and another example of the Fourier requirements not being fulfilled. On fora, you can often find statements like that when an amplifier is rather processing distortion instead of music, you end up with a non-musical sound. And it's in full agreement with our own results and experiences. So now we have to get power to a loudspeaker, and we have to look at the output stage, which is something special. The output impedance of a FET stage depends strongly on the source current flowing to the FETs. And in a class AB power amplifier, it's the most common of the analog amplifiers because of the energy consumption. The source current is a combination of the quiescent current and the current delivered to the load. And when you do some measurements and calculations, you see a curve like this. And on the left-hand side, you see the output impedance. And this is 10 ohms, which is, say, above normal loudspeaker values. And then it decreases with increasing current source, but it never gets that low. At 50 milliamps, it's still in the order of 4 ohms, and at 800, it's about 2 ohms. So the current through the load depends, of course, on the signal amplitude and its phase, because these together determine the output voltage at any moment in time during the cycle. And the output impedance is not to be neglected compared to the impedance of ordinary loudspeakers. And it varies with the amplitude and phase of the output signal, as it will illustrate now, because the signal passes through all phases. This is, say, an N-channel FET, this is a P-channel FET, and the signal goes positive, negative, and it has to pass this area. So when you're, say, close to the zero crossing, your impedance is very high, and of course you can improve this by giving it a quiescent current. But when you continue, you end up as class E amplifier. But you keep in mind that the output impedance, at the moment, the load acts as a voltage divider. And even if that load would be purely resistive, it would not be a constant factor. You can see, okay, this is the amplifier. Ideally, we have an output impedance, then we have a load, and we have the feedback, and we assume that RT and RT1 and RT2 are far larger than the loading. Then you get this voltage division between these two. And you can put an equation, and this is the effective open loop, and this is the open loop before and at this point, which is actually important for the operating of the amplifier. It's different, and when this varies, this factor also varies, and even if Z load would be a constant, it would still have this variance. So the attenuation is not a constant, and therefore your effective open loop you have to use in your feedback equation is not a constant either. But we have an additional effect. We have already seen that due to the nonlinearity of the operating lines, the open loop gain is not a constant, but this effect increases the variability even more. So, and law of conservation of misery, the load is rarely ohmic. It is not only resistive, but it has a frequency dependency in magnitude and phase. And you can easily illustrate that by measuring a loudspeaker in a housing, and this is for a closed box. And you see here that the impedance, the modulus, varies quite strongly over the entire frequency range that you have to use it. This is, say, the basic resonance, but the impedance, the nominal is 4 ohms, but the peak value is more than 17 ohms. And its phase varies between something like plus and minus 40 degrees. And with base reflex systems, the fun becomes even larger. We have these two peaks. We have the crossover peak, and the peak value is more than 25 ohms for an 8 ohm loudspeakers. And the phase varies anywhere between minus 35 and plus 43 degrees. So if you want to call this a resistor, well, you're a bit way off. But what's even worse, the voltage and current can have opposite phases. When I have a phase difference between voltage and current, then you can situations where they are in antiphase. And that is the problem with class AB amplifiers, because in class AB amplifier, basically you assume that either the positive or the negative part conducts. And because of the control circuit, the overlap is only small. And when the two are in opposite phase, then the current says, I want to open the lower part, and the voltage says, I want to open the positive part. And that can't happen at the same time. So that gives problems, and it means that feedback cannot correct this, because having both transistors conducting is prohibited because in the class AB design. So if you then look at what happens to the crossover distortion, you see that it enhances when you do the measurement with a, say, an ohmic load. You get these hubbles, what you want to call it. But when you have a complex load, it's first of all the position shifts, and it becomes, say, more irritating. And then usually people measure an amplifier with a pure resistor as its load. Do you still think that this kind of measurement will yield reliable result for the actual perceptual performance? How naive can you be? So we have some important intermediate results. First of all, the output impedance of fed power output stages can be high with respect to the loudspeaker impedances. Feedback can strongly reduce its overall effect, but that's for the closed loop, but this is not the case for the open loop output impedance. And the open loop output impedance is important for the effective mu. So because the effective open loop gain reduces around the zero crossing, you get, especially where you need it most, you get lower value, so you get less suppression of the crossover distortion. So this effect emphasizes the crossover distortion. So the question is, where is feedback where you need it? So the only way to resolve this is the strong reduction of the open loop output impedance by other techniques, and we'll have a look at that later. And we have to keep in mind that class AB power amplifiers have specific problems when voltage occurrence with loudspeakers are not in phase. And you can counteract that by increasing the quiescent current. And then, of course, you end up in class A. Or you can do the other way around, making the loudspeaker impedance as much as possible resistive, and thus to minimize the phase differences. And this is doable, as we will see later. But what are the consequences for the feedback calculations? Well, to calculate the properties of the amplifier in closed loop, mu is required, but an analytical equation for mu is not available. So we are forced to use approximations, but how can we be sure that these are accurate enough to predict the perceived quality of amplifiers? Apart from a large number of options to implement local and global feedback, we also have choices for the numerous parameter settings, so there is a serious problems. And to name a few of those, low frequency open loop amplification, small signal levels, non-linearity of the individual amplification stages, global feedback factor, local feedback factor for individual amplification stages, the color frequency of the open loop amplification, etc., etc. Well, in the presentation that you can download from the website, you can see it all. So these all influence the properties of the amplifier. And an example will be the temporal resolution, because one of my statements is that we have to pay far more attention to the temporal properties of systems. And on the left-hand side, you see, say, when you have a close to an unstable amplifier, that you get a huge time smear. And by better design, you get something on the right-hand side. But if you would measure these up to 20 kilohertz, both amplifiers would be virtually identical. And well, we can wonder whether this oscillation or closed oscillation is audible. Well, in 2017, we had a workshop at the Berlin AES convention. And then we had a comparison between tweeters, and one of the tweeters is shown on the right-hand side. And it showed a bit similar properties like the left-hand side curve, and it was clearly audible. This tweeter was the worst from the comparison. So the consequence of all this is that there are at least as many different amplifiers with feedback can be built as a species of dogs. We call all these animals dogs. But There are differences. This is what we call a good dog, and this is called a bad dog. So can we say what should be done? Well, there is no such things as the feedback, just as there's no such animal as the dog. So between none and up into the stratosphere, such a wide realm of different ways to implement local and global feedback at an enormous range of parameters. So the discussion, the feedback or not the feedback, is next to useless because it's not either or. And the variability is you get when you have a good designed amplifier with feedback compared to an amplifier with bad designed feedback. That is the basis of the paradoxes mentioned below. So, but the resolution of these paradoxes lies not by just more feedback. So we'll need a extension of the theory, and we need a far more extended and detailed theory of feedback in order to be able to predict the perceptual properties of amplifiers in closed loop for the reproducing of music. That's what's important to me anyway. I listen to music, I'm a big music lover, and I want to have as little contributions from the system as possible. But the common calculation is way too simple and is not able to do this. Is why we have these paradoxes, and we have distortion figures which are all over the place, and they don't always predict what we're hearing. And such a theory should also be able to deliver design rules for amplifier with a high perceptual quality. But that such a theory should also be able to describe the interaction between the different limitations and artifacts. And the measurement should be done under realistic conditions, which are far different from the operating conditions of which the equipment is normally used. So we have to do it in a different way. And if I have time, I'll spend some words on it. And we need test signals which resemble far more those of music. I already showed that with the triangular sine wave, or the sine wave with the triangular modulation, already artifacts occur which are you can't see with continuous waves, but music is very variable too, so you can be sure that these will also occur when you play music. And so this testing will have to be multispectral and span a wide dynamic range, including rapid changes in time. But an extended theory of feedback will take quite some time to materialize, and don't expect it to come from me. It's way above my mathematical capabilities. And the same for more realistic test signals, which is why I think that listening tests are far more important than many people think. But how can we progress? Well, my way to tackle this is I'll give a working hypothesis. When we design an amplifier of which the open loop properties are as much as possible in agreement with the requirements of the Fourier theory, we will only need small approximations. And it's reasonable to assume that the realized properties will be close to the desired ones and calculated ones. But it's still an assumption. How can we do that? Well, we have to have some requirements for the amplifier design. So we have to use individual amplification stages which are as much as possible linear. And we need a power output stage with as low as possible and constant output impedance. And we'll need a constant open loop amplification in the entire audio band and the first order low pass filter response above it. And because that will also give a minimal contribution to the time smear, we will need as stable as possible power supply voltages. And often neglected, a power supply which is able to deliver the maximum required currents, which are needed under realistic conditions. So with real loudspeaker impedances and with real music signals. This is all possible. And how are we going to tackle this? And which are the points to watch? Well, my first of all, warning, don't look at harmonic distortion only. Harmonic distortion is one, but in my experience is one of the least important ones. There are other artifacts which generate unrest in sound, like the local internal detection, the masked micro details, amongst by the interaction between the DNA, and deteriorate the perceived quality. But you won't measure them with continuous sine waves. But they're usually far more irritating to the ear. So we have a saying in Dutch, it's better to prevent than it is to cure. And so my approach is avoid all these DNA as much as possible from the start. And that's in line with the working hypothesis. So the four important aspects to focus on are the linearization of the individual amplification stages, the low and constant output impedance of the power output stage, making the loudspeaker impedance as much as possible resistive and stable power supply voltages with sufficient peak current capacity. And we'll have a look at that later. Well, we have developed two ways to linearize the individual amplification stages. In their properties, they're virtually equivalent, except that one is not easy to implement, but using a design which I call a transistor, it's very simple, as a transistor can take the place of a transistor. And we'll show that by calculate the properties of a transistor and transistor amplification stage, and we'll use the result of the harmonic distortion without feedback as a measure of their linearity. Well, this is the amplification stage, very simple. It has the design goal of 10 times 35-volt power supply, and we'll compare the transistor and transistor stages. So no feedback has been applied, it's just what this individual amplification stage does. And we'll look at the harmonic distortion of these. The vertical scale is 20 dB per division. This is of course, the signal you put in, and these are the harmonics. I hope that I can. And you see that goes pretty far before you come below the minus 100 dB. And the amplification is 9.7 times 9. And the transistor is not an op-amp feedback. It's just a circuit using discrete components. It behaves as a transistor, but it has significantly better properties. And you can see that by looking at the results of the distortion. You see we still get harmonics, but the third is already below minus 100 dB. And also the amplification is far closer to the design value. And the second harmonic is 42 dB lower than of the transistor stage. And the amplification is far closer to design value. And keep in mind that internal local detection is also responsible for HF detection. Because the feedback factor decreases with increasing frequencies, global feedback can suppress this less and less. So it's better to avoid HF detection by making the individual amplification stages as linear as possible, because a linear stage cannot generate local detection. Okay, so that's the way to tackle the linearity of the amplification stages. And the output impedance of a FET output stage, well, we made a different design. This is 0 to 500 milliamps, and this is the original value of the FET. But by doing a bit different, we managed to come down to this, and it's about 30 times lower. And here we are in the ohms region, and here we are in the less than 0.1 ohm, if I got it right, 0.16 or something. At least there's about 30 times lower. And the strong reduction of the FET impedance reduces the crossover distortion significantly. Now, when I was still in my diapers, I think there was a person called Sobel or Zobel, I don't know how to pronounce it, but he basically said, well, I don't like these impedance variations of loudspeakers. So he designed several networks you can put parallel to a loudspeaker to make it more ohmic. So I have to give credit to him. And this part is for the coil inductance. By putting this parallel, you can eliminate that, and this is the resonance compensation. And when you do that, you can measure the impedances before and after. This is the original one, and with the blue arrows are indicated after. And it also works for the phase. The original phase was about here, and after compensation, you end up with this. So the point is that by using such a network in parallel to your loudspeaker unit, you end up roughly at the DC resistance of the loudspeaker. You can't get any lower. You always have a DC resistance of loudspeakers until we can make loudspeakers of superconductors, which I doubt I'll live to see. So it means that output impedances below 0.1 ohms are virtually useless because they won't give any more damping. So damping factors of over 80, say, are over the top. Values above these are usually achieved by using very high feedback factors, and that usually gives more harm than good. So, and always keep in mind that the feedback factor is not identical for all stages, and especially for the input stage differential is amplified as much as the input signal. So there's no feedback here actually at all. So it's very important that you keep the distortion and the DNA of the subtraction circuit as low as possible. And when you manage to keep the open loop cutoff frequency above 20 kilohertz, the open loop amplification is the same for all audio frequencies. And thus there are no interactions between amplitude and frequency domains. So these cannot help you or bug you better. It's also helpful to minimize the time smear to keep the recovery times after overload short. So my advice is choose an order of the filtering, the open loop gain, which generates as little as possible time smear. And the best is a first order low pass filter. And you can do that also by give compensation for parasitic filtering and the selection of the cutoff frequency. I know there are designers who say, well, I want to use a high feedback factor, so I use all kind of clever tricks to stay away from the -1 point in the Nyquist plot, but they usually have a very bad time behavior. So my advice, don't maximize the open loop amplification, and it leads to a significant increase in the DNA in general. So not only the distortion, look at all the different ways that artifacts can generate. Then, certainly last but not least, the power supply is often treated as a stepchild. The power supply is crucial for the perceived quality of electronic equipment. It's because it's mostly expensive. Manufacturers tend to say save cost on that, but it's not the right way to do it. Because at several points, its limitations can generate specific artifacts. While the ingress of the power rails voltage fluctuation has already been mentioned, but my statement is no apparatus is better than its power supply, and we will look at the differences and the consequences. There are companies in Holland which can upgrade your equipment. When you take it, the first thing they do is take out the power supply originally designed in the system. So let's start with the transformer rectifier buffer capacitors. Well, this is probably standard for everybody. You have AC, and then you have a transformer, two-phase rectifier, and then you have the buffer capacity. And I'll show the graphs and try to illustrate it. That's too fast. you have to keep in mind that the voltage from the transformer has to rise above the voltage across the buffer capacitors. So the time window available to charge the buffer capacitor is significantly shorter than half of the cycle time of the grid frequency. And consequently, the peak current is far higher than the average current taken by the load. Well, you can see it here. Blue is the rectified voltage from the transformer. Yellow is the voltage across the buffer capacitor. And green is the current from the transformer to charge the buffer capacitor. And you have to keep in mind that this scale for the blue and gray and green is the same. So this is 40 volts and 40 amps. And you see that the peak current is 4.59 amps for an average of 1 amp. And when you get to the 2 amp, then you see that you have a bit more time for the current to charge the buffer capacitors, but it's still 7.26 amps. So there is a significant ratio between the peak current and the average current. And you see the effect of the buffer capacitors. Here we have almost 30 volts on the buffer capacitors, and here we have 26.67. So even the doubling the current means that you have a significant drop in the voltage that's available for the amplifier. And then you must be sure that the power supply must be able to provide sufficient current under all conditions. In many cases, the resistance of the transformer coil results in a too large voltage drop during the charging of the capacitors, and with low frequencies, the recharging frequencies which are present in the music signal. When I have, for example, a 20 Hertz signal, that means that that is 1/2 of it is longer than the recharging of the capacitors, which means basically that you're almost driving a DC signal, DC current from the buffer capacitors. So when it works for 1 kilohertz, that doesn't mean it works for 20 hertz. And you have to keep in mind that the current of the outputs are determined by the signal, the volume control, and the impedance of the load. And that can be far larger than the average current. So the buffer capacitors must be pretty big in order to have sufficient capacitors to bridge the time in between the charging parts. So between here and here, the amplifier just draws from the capacitors. So it must be able to have sufficient capacity there. And what happens is that the transformers are expensive, so we want to use as small ones possible. We want to use small buffer capacitors because those take up a lot of space. They're also expensive. So that's why they often are designed too small. Don't design it on the average values. You have to design it on the peak values. And the fluctuations will ingress into the signal. So regulated voltages with a very low internal impedance are required for amplifiers. And the DC coupling will also result in, as a passing on of the ingress of whatever misery on the power supply rails to further stages. So decoupling of the supply rates for the different stages is recommended. Well, I want to use spend some time on the test measurement. So we have to use more complex signals than sinusoids. New signals need to be developed, but it won't be available on short notice. So unless you apply impedance compensation, you have to use realistic loads for simulation of a real loudspeaker. And don't use a resistor then. Tone burst can be useful because of the short start and stop times. Use many different frequencies, not just 1 kilohertz. And use a wide range of amplitudes. Certainly for class A, B amplifiers, you can see that their behavior at small signal is often worse than for large signals. And don't only look at the frequency response, but also at the impulse response to determine the time smear of it. Okay, now come to some conclusions. I'm going through these pretty fast. It should be most of them pretty clear. And the presentation, PDF on the website, you can download it and read through it on your ease. So we should get rid of the Fourier theory approach. Major consequences that properties of most audio systems cannot be determined using continuous sine waves. It also result in design guidelines which decrease the perceived quality because of differences with music. And you have to design audio with respect to the Fourier boundary conditions, and that leads to perceptually better systems. And we've shown that the guidelines for such a design approach are feasible. And the common theory of feedback is for description of systems is only a crude approximation of reality. And the most obvious pitfall is the impossibility to describe the open loop properties. And so description of the closed loop properties is out of the question, because the open loop properties are in the equation. So if you can't describe that, you can't describe the closed loop properties. And well, at least for me, it's impossible to predict whether the still necessary approximations are accurate enough to predict the perceived quality of the system. So use a design which, as much as possible, avoids the generation of DNA inside the loop, and it yields systems with a high perceived quality, because I can be doing that, and it's confirmed by several of our clients. And it might come as a big surprise, but linearization of the individual amplification stages improve the perceived quality significantly, because linear stages cannot generate DNA. So you avoid it from the beginning. And well, actually, one of our most recent developments again proved this statement. So the reduction of the open loop output impedance of the power stage results in increase in the perceived quality. And it's because the best way to counteract crossover distortion is one of the most irritating artifacts of Class B amplifiers. And actually, I showed that it had a factor of 30 reduction, and we are still working to see if we can get it even further down. So there are many other artifacts than harmonic distortion. Don't focus on it only. And the quality of the power supply is crucial for the total quality of any system. No system is better than its power supply. Don't try to do it cheap. That's the wrong way. And another field that is often neglected is the interaction between the power amplifier and the loudspeaker. It needs more attention than it's common. You have to look at the combination in a holistic way, because together amplifier and loudspeakers have to do the job. You can't get sound out of an amplifier, and you can't get sound of a loudspeaker unless you couple them. So you have to also look at their interaction. And well, to our experience, the use of impedance compensation is highly recommended. It creates a load for the amplifier which resembles the design load as much as possible. And you just eliminate all the problems that I illustrated that you can get with a Class AB amplifier with large phase differences between voltage and current. And it's feasible with mobile networks. The design can be automated, doing this already for tens of years. And when I first began, I tried to do it just by paper and pencil. Well, I soon said, well, this is a bit too complex. So I just wrote a computer program and said, okay, this is the impedance measured, and calculate now the Zobel network. I've had a presentation, I think in '94 for the Amsterdam AES convention about this. And the measurements we do should be built on a completely different concept than we do now. The test signal should resemble music much closer, and loads should be more realistic. Resistor for a common loudspeaker is nowhere near unless you apply impedance compensation. And the temporal property should be an essential part of the test. I've been yelling already for, I think, 45 years that the time properties of systems is very important for the perceptual effects. Well, gradually, it takes some time. More people say, well, he is not as mad as he looks. He might have some points there. Okay, then close out. I didn't mention it explicitly, but I would like to emphasize that all amplifiers, all the electronics built by Temporal Coherence only use discrete components. And the reason is that only in that way we can impose the desired properties on the design. If you use an integrated circuit, you're stuck with the design philosophy of the manufacturer, and that's often quite different from ours. Example, the differential stage of an input of an op-amp is usually done by making the emitters couple directly, which is very effective for the low frequency open loop gain, but it's an excellent way to introduce measure you'll never get rid of anymore. So don't be surprised that our differential stages look completely different, and should not come as a surprise that these are based on transistors. And always keep in mind that DNA are in the DNA of electronics. And we can have some discussion now. At this is our website. It's both in Dutch and an English version. If on the upper right-hand corner you see EN, and that means that you get to the English version, and you can download the PDF of this presentation there, so you can have a look at it at ease. So now I hand over to the chairman of the night.
Hans, thank you ever so much. That was a brilliant talk. A lot in there, an awful lot, which was great. I'm just monitoring both the chat and the Q&A. So thank you very much for the reference to the link there. So just to clarify, the slides from today are available to download from this website?
Yeah.
Ideal.
But you go to papers or so, and well, you should be able to find it. And if you can't find it, you can send an email to info@temporalcoherence.nl, and I'll send it to you. But I think it should be doable. And for those who want to learn Dutch, it's also a Dutch version available.
Excellent. Okay, thank you very much for that, for clarifying. Okay, so there appears to be a burning question, and that is, what is a transistor?
Yeah, well, that's for the time being a secret of the company. It took quite some development and thinking, so I'm not going to give that away yet.
So that's IP.
Yeah, but
absolutely understood. We don't want to give that away because we would like to post this presentation on YouTube, so we're not going to talk about that for now.
Okay.
Okay. We had a point from let me have a look. Sorry, as I say, just going across two chats. Just so that everyone's aware, more than happy to take questions in the chat, or ideally in the question and answer, so I can just work through them. And so, one from Jamie Angus. Can one not design internal circuits that have good power supply rejection? I guess thus nullifying the issue of having consistent power supply.
Well, maybe you could, but you would make the amplifier itself more complex, where you can basically, if you have a good regulated power supply, you can avoid it. So I'm just a simple physicist, and my approach is, well, if you can avoid it, well, why not? Some people say, well, you don't need loudspeaker impedance compensation because the amplifier should be able to handle it. Yeah, well, that might be the case, but the amplifier will behave not as good when it behaves with an impedance corrected loudspeaker. So yeah, the simple approach is, well, if you can avoid it, avoid it.
So looking at it on balance, then would it be fair to say that a stable power supply would be more easily um, created than the type of thing that you would have to put together in order to reject a dodgy
I think
power
so.
supply? Mm.
Actually, well, we use regulated power supplies already for decades, and well, then you still have the high impedance of the collector, but when there is no rubbish on the power supply line, it can't pass anything through because it's not there.
Mm. Mm. Okay, thank you. Continuing. So, would a modulated signal approach be a better test signal? For example, like the modulation transfer function approach.
Well, anything than say continuous sine wave is probably better, but one of the things that really need is, say, strong and fast fluctuations in amplitude. I've shown that
Yeah,
800 hertz signal, and okay, it's not even very fast, but still you can easily see then what happens at the low frequency rubbish. So one of the things that most systems have problems with is attack. One of my standard tests, listening tests, is say the grand piano, the left hand. When they start from bum, well, most systems make something of it which has only a close resemblance of it. If you have percussion, well, one of my other ones is, say, the Turkish drum. Well, I'm a frequent visitor of the Concertgebouw in Amsterdam, and there I hear a completely different Turkish drum than from many systems. That's also part of because the temporal properties. So you have to look at not only at the modulation, but also say at things like attack, time smear, and interference with it. So it's I don't know exactly at the moment what kind of test signals would be best. But I'm not the only one, and many people are working in audio, so they can also think what better ideas that could be generated. But say when I listen, say attack and the dynamics are very important for the perceptual quality.
Okay, thank you. Okay, there's some rather involved questions coming in on the Q&A, which is great. However, just quickly, is there again, this is from Jamie Angus, is there a power dissipation issue associated with the Zobel network?
What?
A power dissipation issue associated with the Zobel network?
Yes. Well, not only power, but when you look at, say, the inductor, it's usually, say, has a core. So you have to watch out that you don't get core saturation. So you have to make sure that the properties of the components will remain in your whole operating range, what you hope them to be. So you can't use a very simple cheap coil in an impedance compensation for a woofer of 50 watts or so. That's not going to work well. So yes, and well, for the resistors, you shouldn't use a quarter watt resistors there. You should calculate how much they get. So yeah, it's absolutely a power issue, but also a current issue.
Okay, thank you. Okay, I'm going to move to an involved question. Hans, I wonder if you can see the Q&A as well, or is it just me that's able to see this?
No, I can't see it. So
Okay, that's fine. Well, if you'd like me to repeat anything, I will do my level best to communicate from attendees to yourself. So, okay, here we go. A great many questions arise from this challenging talk, but I would like to take you up on 2 points particularly. Firstly, you say many times that feedback theory requires the forward path gain, mu, to be constant, but no feedback controlled system, whether it be an audio amplifier or a spacecraft navigation system, far more complex in terms of its feedback theory, requires or remotely relies on such an assumption. The whole point of applying feedback is because mu is not constant. Of course, the forward path gain needs to be at all times sufficient to give us adequate closed-loop linearity, including when it is inevitably reduced by all the various miseries you mention, such as crossover effects, bandwidth limitations, and so on. Okay. Secondly, can we please discuss your description of the class A or B output stage in conjunction with a reactive load? I don't disagree that Zobel networks may be helpful, but your description of what happens in the output stage with a reactive load is quite wrong, according to the questioner.
well, first of all, the open loop gain, which also is the function of the signal at all points in the whole design, is not a constant. So you would need an analytical description of it in order to fill it into the feedback equation. Well, I haven't ever seen one which is a good description of the reality. So if I, let's say, let's take 3 amplification stages, forget about the power at the moment, yeah, then I could basically describe each of the operating lines by, say, a Taylor series, and well, up to the, let's say, 10th harmonic, which means that I would have 10 times 10 times 10, 1,000 parameters to describe it. Well, good luck with it. Then you have the frequency dependency also, which is somewhere in the whole chain happening, which influences this all. Well, I haven't got a clue how you could make an analytical description of it. So you have to make assumptions. And then the big question is, which assumptions are acceptable and will not give any still reasonable, acceptable results? Well, I don't know. Because we don't, it's a chicken and egg problem. We have a non-analytical description or an approximation of mu, but an approximation is an approximation. You know, how well can you describe it? Well, I don't know. But if somebody has a good way to find a good description of an open loop gain under realistic conditions, well, I'm happy to hear it. Don't expect me to do it. I'm just a simple physicist and not a mathematician who deserves an Abel Prize. So, but approximations is always the big question: is the approximation sufficient enough? Well, I don't know. So my approach is simple: make it all as good as possible before applying feedback. Well, what about the power amplifier in class AB? Well, I've seen just by looking at, say, putting in a class AB amplifier with a non-resistive load, that these effects occur. So I'm not saying that I'm right or wrong. I do. It also depends on many of the parameters that you have. But if your voltage on the output stage is positive and the current is negative, it gives friction, for lack of a better word, in the feedback loop. And you see it in the output result. And well, the best way that I have found is to apply the Zobel networks. When I started this, an acquaintance of mine who has, well, say that's golden ears, that, well, okay, please come to my place and I'll show the amplifier with and without. And it was then even a simple Zobel network. Within 30 seconds, he said, well, you're absolutely right, that this makes a major difference. And that's why we developed it. And so I can't decide from here whether who is right or who is wrong. What I know is my ears tell me that if I have an amplifier and a loudspeaker, which is impedance compensated, it is generally perceptual better.
Okay, thank you very much. I think just following on from this, I have another point following on, which is if the low current is out of phase with the voltage, all that happens is the handover of current from the upper device to the lower one happens at a different point on the waveform. Crossover occurs whenever the output stage current reverses, regardless of what the output voltage may be, and there is no requirement for the two devices to be on simultaneously, unless this is deliberately done to bias the stage into class A, B, or A.
Well, if there's a phase
Agreeable?
difference, if there is a phase difference between voltage and current, then close to the zero crossing, they can the positive could be the voltage and the negative could be the current and vice versa. So this happens. And of course, the range where this taking over occurs is larger when the quiescence current is higher, which is why class A has no problem with it at all. But the law of conservation of misery, class A is a heating device in your living room. So the best way to avoid it is that you get this phase difference between voltage and current. And that's achieved when you have a pure resistive load.
Right. Okay. Okay, good. Right. Question from Bob Young. Have you tried music as a test signal? For instance, there's an example here, listen, sound checks, test system. So just simply using musical content of, well, you bring an example of a grand piano, and Jamie Angus points out maybe a harpsichord would be a good test signal as well. Are there any sort of go-tos that you've actually used where you've thought, well, this is exactly what I need for this particular system in terms of evaluating the fidelity of the system overall?
Yeah. Well, yes and no. No is I don't know how, even if I would use such signals, how I should interpret the output of the measurement device. So yes, fortunately we have a couple of people with golden and some even platinum ears, which are very good listeners. And they have pointed several times at issues in our systems and say, well, but problem is they're not technical people. So they can, the musicians, they know very well, can listen. Well, it's even alarming to me. But they say, yeah, well, there is something wrong here. And then for us was to find out what, but they were always right. And well, I don't approach their level of, say, sound listening, but I'm getting closer and I now hear things that I couldn't distinguish, say, 20 years ago. But the human hearing is still the best measurement device for this. And that's in line with what Maanen Kunshur at several AES convention has shown and illustrated with his evaluations.
Understood. Okay, thank you. I'm just looking across both the chat and the Q&A. There was a question. Where is it? Yes. Paulo asks, can you comment on the concept of the blameless amplifier that was formulated, as far as the questioner can remember, by Douglas Self?
Well, I once heard a lecture of Self at the AES convention, and one of my comments was that he did not take into account the non-resistive load of the loudspeaker to the amplifier. And
so this point is critical then.
to me, it is.
Yeah.
Um,
Okay.
but to be honest, I've heard very expensive amplifiers and very expensive loudspeakers at the Dutch audio event a week and a half ago. We have a system 1.4 million euros, which is about the same in pounds. And I hear things which are quite different from what I hear in the conceptual. I'm sorry. So the blameless amplifier, well, I wouldn't dare to say that there are no artifacts in our equipment.
Right, yeah, okay. Yeah. I mean, yeah, it makes sense. Okay, just a correction. It was my mistake, my misinterpretation of that previous point raised by Bob Young. The listen sound check is a measurement system, not a specific listening test or a track. So apologies about that. Maybe listen sound check is something to perhaps have a look at as a suggestion. An interesting one from Keith Holland. Could a differential amplifier be used to listen to the difference between the input and output using music?
Well, that question has come up multiple times in my lifetime. The point is that well, you can have an input signal, have an output signal, and you take those two and you determine the difference. Well, that is very hard to do because usually there is some slight phase difference between the input and the output of the device on the test. And you have to compensate for that in order to avoid that you interpret just a small phase shift as an artifact. Well, we've looked at this several times, and the effects that we are looking at are way too small to get the result in this way. It's been suggested many times, and it all say stranded on the problem: how do you compensate for the non-idealities of the device on the test that you're not really interested in? Say a phase shift of only say 1 degree at the 20 kilohertz is not something which is very audible compared to what loudspeakers do. But if you take the difference, then it's a huge contribution. So it's nobody has ever succeeded, to the best of my knowledge, to achieve such a measurement, which is useful and can be interpreted.
Interesting. All right. I wonder, just off the top of my head, have you come across the M noise?
Well, noise is in general not a problem in our systems.
Just M noise, the specific AES signal for testing.
No, we haven't used that.
No,
But,
okay, cool. No worries at all. Okay, again, just looking through. Okay. My tracker pad's giving up the ghost. Here we go. That's better. Spice. There was a question about spice and I can't find it now. Folks, if anyone wants to post another question to Hans, please do so while I'm looking for. Oh, here we go. Any comment on an awareness of audio applications of spice modeling, so circuit simulation? Is it a step in the direction of more complete analysis for nonlinear effects? Is it used in designing computers' digital circuits? I don't understand the relevance of that last part entirely, but have you used any simulation software for this kind of stuff?
Well, hardly. I'm very old-fashioned. I can write my own programs, so many of the things I want to try out don't really work well in this kind of software. So I write my own program so I can do any calculation I want on it, and I'm senior enough to have to learn the program myself. So I take all the details that I think are important for the operation and the properties of the design, and I do the calculations myself. Same for the impedance compensation. I wrote the program myself. I say, okay, this is the measured impedance curve, and well, in the 94 presentation, I said, well, I designed an 8-parameter model for an electrodynamic loudspeaker in a closed housing, and then the computer calculates those parameters, and it even predicts the phase behavior of the loudspeaker actually. So it gives me some flexibility, and I can always know what I'm doing because I write the program myself. So it's, that's an advantage of my training in days that computers still took up 3 big holes.
Okay. All right. Well, folks, I am going to put out a last call for questions, and just have a quick review of the chat just to make sure I haven't missed anything. Here we go. Okay, point raised. Well, a couple of points raised. Do apologize, Hans. It's basically the question of space and not knowing how good it is for nonlinear modeling at the current state. And then a point from Gary: sound in rooms is not a one-to-one relationship to the audio signal.
Sorry,
Fair
say that
point.
again.
It isn't. Sorry, sound in rooms is not a one-to-one relationship to the audio signal. It is an
Okay, that's
acoustic
right.
event, not a binaural event going into the ears directly. So as such, there's no direct relationship between signal and audibility.
Well,
From a person-to-person perspective, I guess that's extremely true.
well, I have to make some comments about it.
Please.
The point is that there certainly when we talk about attack, say the instantaneous signal is far closer to the original before the reflections come in. So the direct sound reaching the listener is, say, quite different. It's not as much dependent on the room as many people think. And there's even a Dutch manufacturer who uses this by making his loudspeakers very directive. So the reflections from the room are very, very minor. So that you must take into account the time effects, and that's very complex. And I know, and that people who know a lot about, say, room acoustics, etc. But if you look at the room acoustics just from continuous wave performance, you get a result which is not always very pleasant to listen to. So the direct sound and the indirect sound are things that you have to look at separately. So it's more complex, but to my experience, certainly when you talk about time behavior, the properties of the direct sound and the impulse response of the system are very important for the perceived quality. So I'm not saying that the person is wrong or think there are more nuances than just looking at say yes or no. Did I make my point clear? Or
I believe so. Okay. So I think, well, we are coming up to pretty much the end of our scheduled allotted time here. So long as there aren't any last minute questions from anyone? Just again,
Okay,
monitoring
I'm
the
going to
chat.
make two small statements. First of all,
Please, by all means.
anybody who's visiting the Netherlands is welcome to listen in my place to what I have standing there. Secondly, if people still have questions afterwards, they can send an email to info@temporalcoherence.nl and I'll see what I can do. I don't know everything either, but of course I can give it a try.
That's a very two very gracious offers there, Hans. Thank you very much indeed. And well, I would like to say thank you very much, Hans, again for taking this presentation. It's been extremely interesting, extremely insightful, and I'm sure a lot of people, unfortunately, a few people couldn't make this rescheduled time. However, there's been a lot of interest in accessing a recording of the sessions, so hopefully, you know, it'll be there as a resource for years to come when it gets uploaded. And I can tell you, if you're not seeing the chat, the thanks are coming in. And Jamie, we have a raised hand. We no longer have a raised hand. We have a nope. Two raised hands. People are raising hands. I don't know why. Oh no, it's okay. Right, okay. Hans,
well,
as I say,
my regards to everybody in the UK that have been attended, and I know because I've met quite a lot during the AES conventions.
Splendid. Thank you very much indeed, Hans. And as I say, loads of thanks coming in on the chat. So I'll draw this to a close. I will end the session. And once again, Hans, absolutely delighted to have you here for the presentation. We'll look forward to hearing more from yourself and Temporal Coherence as we go forward.
Well, my pleasure. Enjoyed doing it.
Really enjoyed it. Thank you again.
No,
all right, everyone. Thank you so much for being here. Take the best care.
Bye-bye.